Hello, my name is Jonathan Medina, and today I will be presenting on ERACAN, defending against an emerging CAN threat model. To begin, let's define ERACAN before we get into its architecture, capabilities, and features. ERACAN is a emerging defense model for CAN systems. Its primary goal is to mitigate security threats by CRAM and the ERAM attack models, which we will be going over shortly. Well, if ERACAN is supposed to protect CAN, what is CAN? Well, let's learn a little about CAN before we move on. CAN stands for Controller Area Network. It's a communication protocol that is used in a variety of equipment, and it allows for multiple nodes in the system to talk to each other. Well, where is CAN bus used? Well, it's used in a variety of things: vehicles, robots, aviation, building automation, and medical equipment. And there's other stuff too. Um, the most common place where we might find the CAN bus will be in a car. And as you can see in this picture I have up here, we can see a little diagram of it. So it pretty much allows the multiple nodes or computers in a car to talk to each other. And, maybe your ECU, your fuel management system, transmission module, ABS, HVAC, all these kinds of things need to talk to each other. And they will do that through the CAN bus. As we can see up here, there's an OBD2 port, which is the most common way that most of us will interact with the CAN bus. I have it diagrammed out here. I think the specific pinouts for a Subaru, but yeah, the pinout I believe differs by manufacturer. Well, what about the origin of CAN? So we know where we're using it, but where did it come from? Well, it was first developed by Bosch back in the 80s, and it was intended for use in vehicles like cars. And the purpose of this protocol was for it to be fast, efficient, and cheap. And then shortly it became the standard by the late 80s. Uh, Philips and Intel were making chips for using CAN controllers, so it picked up quite quick. What about our security concerns with CAN? Well, when it first came out, security wasn't as big of a concern as it is nowadays. There wasn't. It was thought that physical security was going to be sufficient to protect your systems. That the only allowed personnel like technicians or your certified mechanic or somebody along those lines was going to be the person with access to these critical things. Um, because of this, there's little security for it. Like, it has no encryption, and obviously because of the time, wireless technologies weren't as abundant as they are today. So there's also no built-in protection for any wireless attacks. Um, Now we have the CAN architecture. So in every device in the CAN bus or every node, Well, every device is called a node, and in every node, there's a few parts. So we have, if you look at this diagram I have down here, you have a node, which has a CPU, a CAN controller, and a transmitter. The CPU, well, it's the processor, processes our data. The CAN controller manages the communications, and the transceiver sends and receives messages from the other nodes. These messages are called frames. And as we can see, I have a little diagram over here of a standard data message. And then this is made up of a few different sections, right? So let's say we have our start frame, SOF, our identifier, our ID, RTR, remote transmission request, IDE, identifier extension. The arrow is not used. We have the DLC, the data length code, our actual data that we're sending right after that. Then we have our cyclic redundancy check right over here. And we have our ACK, or acknowledgement, which we use in other networking technologies as well. There's also the end of frame, EOF, and lastly, the IFS, interframe space. And all of these make up a CAN frame, or a message. Well, now that we learned a little bit about CAN and what it is, what are we protecting against? Well, there's two threat models. There's SCRAM and there's ERACAN. Conventional remote attack model is SCRAM, and ERACAN will be enhanced remote attack model. SCRAM is older. Because of that, it has less capabilities, and its main capabilities are to send and receive messages. These messages do have to be valid messages. And then we have ERACAN. It's newer. Because of that, there's more capabilities. And this one doesn't only send and receive messages, you can craft them, you can change things in them. You have a lot more options with this with this model. Well, let's start with conventional remote attacker model. And these are some of the attacks that are possible with this model. So we have masquerading attacks, valid message reception, valid message transmission, and simultaneous transmission. So pretty much masquerading attacks kind of send a false message, and they try to impersonate as a authenticated sender. So they try to send a message pretending to be one of the nodes that are supposed to be there, and they do that by using the ID in the frame from one of the other modules that are known to be good. Then we'll have valid message reception. They can read data or remote frames after they're fully validated by the CAN control. Valid message transmission. Can send messages, but must follow the protocol rules. So again, the messages that are sent have to follow the protocol rules, but if you do that, then you can send data and false messages, for masquerading attack or other attacks. There's also simultaneous transmission. On this one, the attacker injects a message with the same ID as another node, and to try to gain access. So pretty much it will send the node with the same ID but with a different payload. And because of that, both messages seem to be legit, and there may be some issues with arbitration. For example, like the attacker might send a message with the same ID. So there's a battle for, not a battle, but there is an issue with who is allowed to send at this time and who is not. So that may cause some issues. Now we have ERA, Enhanced Remote Attacker Model. This is the more modern model, and it has a lot more capabilities. It can manipulate and inject signals and messages, and it has access to both the the data link layer and the physical layer. And again, in those two layers, it can read and write. It can craft messages and pulses. It has a lot more capabilities. And some of the attacks that are available for this attack model are arbitration denial. So it blocks legitimate nodes from reaching. It messes with who is allowed to send the message now, or who has which node has the right to send the message. So it pretends to be a different node, and it tries to take its place in who's allowed to send the message next. You have double receive. This one, the last bit of a message, the end of frame, is flipped from a 1 to a 0, causing an error, and the receiver will receive two messages. So it just gets a duplicate. Then you have the freeze doom loop. This one sends an overload frame, which kind of tells the receiver, hey, I need more time. Can you give me more time? The receiver node will say, yeah, sure, here's some more time. And then it gets more time. And then it says that again, hey, I need more time again. Hey, I need more time again. And this can happen a few times, or it can just keep going in a sort of denial of service, right? Because it keeps waiting. Then you have counterfeit frames, where the attacker can send bad messages, counterfeit messages. It can modify the data that is being sent and just send faulty data. Well, to protect against these, we have ERACAN. And ERACAN is a single module connected to the canvas. It also separates traffic between the physical and the data link layers. It's able to detect and classify both CRAM and ARAM attacks, and it's able to be managed by an administrator, so people can manage it and change the configurations. It also supports smart checking, which we will be going over in a little bit. So layer separation, right? Traffic from both the physical layer and the data link layer are separated, and as we can see over here in the little diagram of the OSI model, they're layer 1 and layer 2. And this separation allows for better performance. As we can see here, we have a diagram of kind of the data flow of ERACAN. Well, the physical layer was made a standard with ISO 11892-11898-2 for the CAN physical layer. Before this, both the physical and the data link were in one. They just separated them. Layer 1 is monitored by time digital converter and the analog digital converter. These monitor time events and voltages. Those are TDC and ADC for sure. The TDC monitors and measures the timing of signals from 1 to 0 and 0 to 1. Changes in this can mean that there's an attack taking place. The ADC monitors the voltages, which can also vary in an unexpected manner when being attacked. The data link layer was, again, made a standard by ISO 11898-1, and that's for the data link layer. All monitoring of the data link layer is performed by the CAN controller. And monitoring is done with smart checking to only look for attacks that are possible for whatever application we're using at the time. For example, if this is in a car, we might not need to might not be looking for attacks which are more specific to like planes or buildings. So this way we save the resources as well by not looking for things that are very unlikely to happen for this application. Now, how can ERACAN check if our data is legit, right? How can we even detect these kinds of things? Well, there's some legitimacy check, right? And for this, we have asymmetric checks, edge count checks, authenticity checks, and the GPIO check. The asymmetry check detects pulse injections and sees if there's changes in asymmetry and message transmission. Edge count check checks the TDC measurements to see if there's any more edges to find potential attacks, so changes in voltages. Then we'll have authenticity check, and this one will use the asymmetry of the CRC to check messages and compare the asymmetry from a message to another message that is known to be a trustworthy one. If it changes too much, then it is discarded and it's an attack. And the GPIO check. Because physical access to the CAN bus is the more convenient way to attack this, it'll check and see if there's any injection taking place through the GPIO pins. Changes in voltages or timing may indicate that there's funky stuff going on here. Well, there's all these things, right? And sure, this may be resource intensive, but it only takes a few bytes to do this. So the total memory used can be calculated by 20 bytes for the model parameter, 336 bytes for the message data, and this totals to 356 bytes per ECU. So what about if we have more than one? Like 2? Well, we just multiply by however many we have. 2, 3, 4, 5. Probably it could be more. And there was also some tests performed, right? And this was done both in a test bench and in an actual vehicle. The test bench was a PYNQ Z2 board. Um, and then the ERACAN controller was with Verilog CAN controller, and that is open source. And for the physical vehicle, it was a 2011 Chevy Impala. All right. Now, when an attack is detected, how it is classified into a few categories, right? It can be attacks that fail controller checks, attacks causing errors, attacks failing GPIO check, attacks failing authenticity check, and attacks failing asymmetry or edge cam checks. So attacks that fail the controller checks, those are attacks that cause data corruption and they may cause issues with timing. And they are detected because of the message integrity or issues with timing. Attacks causing errors are attacks that introduce some type of error, and those are detected by measuring the CRC field and the integrity checks. Attacks failing GPIO check are attacks that use the GPIO pins. As mentioned before, it's the most convenient way. And those are detected by the bit period variance and changes in voltage um, because of injection. Attacks failing authenticity check, and those are attacks that are not authorized senders. So pretending to be one of the other nodes. And those can be detected by measuring the CRC field, asymmetry, and comparing it to a known one. So you check the asymmetry for the CRC field, and is this pretty close to is this pretty close to something that we know that is known to be good? And attacks failing asymmetry. And then these are attacks that cause asymmetry or edge count deviations from what it's expected. So kind of like the authenticity check, how that's checked. It's checked, and if it's pretty close to something that it is known to be good, then it is okay. If it varies, then it's probably an attack. So some of the results for these is the CRAM evaluation on the test bed. So there's some attacks that were tested. There's more in the paper. There's actually quite a bit, but I picked some. And those would be the attacks sender identification, the masquerading attack, the environmental impacts, and error handling. So for the sender identification, 50,000 messages were used for the testing. 100 of them were used to build a model, and the rest were built for testing. For this, ERACAN was able to detect 100% of the attacks. The masquerading attack was 10,000 messages, 2,000 were real messages, 8,000 were part of the masquerading attack. And again, it was very successful with 100% accuracy and zero false positives. Environmental impacts. This was done by changing the temperatures of the environment, and those were changed from 18 degrees Celsius or 64 Fahrenheit to 28 Celsius or 82 Fahrenheit. Under these circumstances, it was found that they were 99.975% accurate without the additional authentication. Once additional authentication was enabled, there was a 100% detection rate. And error handling attacks. Um, for this one, there was a 100% detection rate, but only a 0.02% of false positives. For the ARAM framework, again, there was more attacks, and I picked this few for time purposes. Yeah. Um, well, for arbitration denial, there was 100% detection rate, zero false positives. Error injection, there was 100% with 0 false positives. For with volt, there's error injection with the bed timing was 99.8 and 99.9% accurate with 0.04% false positives. Unorthodox frame injection, which is when attacker sends a frame with a longer than expected length. It's usually 8 bytes, maybe 12, something longer. For that, detection rate was 100% with 0% false positive and the freeze doom loop. So again, sends those messages that say like, hey, I need more time, hey, I need more time, and so on and so on. For those, there was also a 100% detection rate, 0 false positives. And in conclusion, we can say, what is ERACAN? A defense system to protect CAN systems. It is lightweight and performance oriented, and it provides a great detection and classification for both the CRAM and ARAM attack models. Thank you for your time. My name is Jonathan Medina. If you have any questions, please leave a comment.